Every second, the world produces hundreds of square feet of particleboard, a material that packs the strength of entire forests into a thin sheet. But what's behind this process? How do you turn a loose mass of chips into a solid board that can handle the weight of heavy furniture? Picture this. From tons of wood chips mixed with resin at temperatures around 400 degrees Fahrenheit and pressure of dozens of pounds per square inch, a solid board is born in just minutes. Resin dosing is critically important and typically runs 6 to 10% of the dry chip weight. The forming machine creates a 3-layer structure. Fine chips on the bottom, coarse and strong in the middle, fine again on top. It's like a sandwich where each layer serves its purpose. The hot press squeezes the chip mass under pressure of dozens of pounds per square inch at 400 degrees Fahrenheit in just a few minutes. During that time, the liquid adhesive transforms into a super strong polymer that locks millions of wood particles together permanently. Stick around till the end. You'll learn a secret almost nobody realizes. Picture a massive particleboard manufacturing plant. Mountains of wood chips and shavings arrive here from sawmills and furniture factories. This is wood processing waste, stuff that used to just get burned or tossed. Now, this waste becomes valuable material. First step, sorting the shavings. Not all shavings are created equal. There's coarse, there's fine, there's dust. Different layers of the board need different fractions. The shavings get fed through a system of sieves and screens, vibrating mesh with different sized openings. Coarse shavings stay on the upper screens. Fine stuff falls through. The finest fraction, almost like sawdust, gets separated out on its own. You end up with 3 main fractions: fine for the outer layers, coarse for the middle layer, and superfine dust, which is often burned as fuel for the plant's boiler. After sorting, the shavings need to be bone dry. Wet shavings won't bond with the resin, so they get sent into massive rotary dryers. These are rotating cylinders tens of meters long, with hot air circulating inside at temperatures up to 300 to nearly 400 degrees Fahrenheit. The chips spiral through the drum, constantly tumbling and releasing moisture. In just a few minutes, moisture drops from 50 to 60% down to 3 to 5%. This is critical. Any higher, and the board won't reach the strength it needs and can warp. After drying, the chips are hot and light as down. They're cooled with an airstream and sent to storage bins. Now comes the key component that'll transform this loose mass of chips into a solid board, the binder. Most often, that's synthetic resins, primarily urea formaldehyde or melamine urea formaldehyde. The sorted chips feed into special continuous mixers. Inside, resin sprays through nozzles, creating a glue mist that coats every particle of wood evenly. Resin dosing is critical and typically runs 6 to 10% of the dry chip weight. Too little resin? The board won't gain strength. Too much? You're wasting an expensive component, plus the board can become too rigid and brittle. Along with the resin, other components may be added. Hardeners that speed up resin polymerization, hydrophobic agents, paraffin emulsions that make the board more moisture resistant, fire retardants for fire-rated boards, dyes. The resin-coated chips, now sticky and ready to bond, are finally ready to become a board. They're transported to a massive forming machine, where scattered particles give birth to a continuous chip mat. This is where the engineering magic of creating the 3-layer structure happens. The forming machine is a complex system that sequentially and with high precision deposits chips onto a moving conveyor belt. First, it creates a perfectly even bottom layer using the finest chip fraction. Right after that, a significantly thicker middle layer goes down on this base, made up of large, sturdy chips. To finish it off, this whole carpet gets covered with another layer of fine particles, creating a mirror image of the bottom layer. This carefully calibrated structure, think sandwich, gives the future board its unique properties. Its smooth, dense outer layers are perfect for further sanding and laminating, while the strong inner layer gives the board the rigidity it needs and the ability to hold fasteners reliably. The formed but still loose mat passes through a prepress where it gets compressed significantly. This pre-pressing removes excess air and shapes it into a form that's convenient for loading into the main press. This is the climax of the entire technological process. The pre-pressed mat, cut into segments of the specified length, feeds into a hot press. This can be either a giant multi-story batch press that simultaneously compresses an entire stack of boards, or a modern continuous belt-type press. Inside the press, the particle mass faces two powerful forces at once. Enormous pressure, reaching dozens of pounds per square inch, compresses the chips, leaving zero gaps between particles. At the same time, the press platens, heated to 400 degrees Fahrenheit, transfer their heat into the mat. This high temperature activates the resin, triggering an irreversible polymerization process. The liquid adhesive instantly transforms into an extremely hard and durable polymer that permanently bonds millions of wood particles together. Press time depends on board thickness and typically lasts just a few minutes. In that brief window, the loose mat becomes a hot, solid, and completely monolithic particle board. Hot panels can't be stacked immediately after pressing. They need gradual cooling to relieve internal thermal stress and prevent warping or distortion down the line. To do this, they're placed in special fan or radial coolers where air blows over them for several hours until they completely cool down and their structure stabilizes. Next up is calibration and sanding, which gives the panel its finished look. The panels pass through multi-head grinding machines where wide abrasive belts remove a thin surface layer, bringing the panel to its exact specified thickness and creating a perfectly smooth surface. This process eliminates any imperfections that might have formed during pressing and ensures dimensional accuracy within fractions of a millimeter. In the final stage, the large production panels are cut into standard commercial formats and their edges are trimmed. Massive circular saws or panel cutting machines slice the panels into standard size sheets, typically around 6.5 by 10 feet, 8 by 4 feet, or other formats depending on the market. The finished product undergoes strict quality control. Here they test its density, bending strength, moisture content, surface quality, and dimensional accuracy. Special instruments measure surface hardness, resistance to delamination, formaldehyde content, a crucial environmental metric. Board samples are tested on tensile machines, checking what kind of load they can handle. Moisture resistance gets tested by submerging samples in water for 24 hours and measuring how much they've swelled. Only quality boards get marked and sent to the warehouse. Each board receives a marking: formaldehyde emission class, density, moisture resistance, production date, batch number. This information is critically important for furniture makers and builders. From there, their journey leads to furniture factories, where they'll transform into the everyday household items we're familiar with, silently demonstrating an amazing journey from worthless chips to a functional and indispensable foundation of our comfort. But the story of Particleboard didn't start yesterday. The first particle boards were invented in Germany in the 1930s. During World War II, Germany faced a severe timber shortage, and engineers searched for ways to use woodworking waste. That's how the idea was born to glue small chips into solid boards. After the war, the technology spread rapidly worldwide. The 50s and 60s saw a real particle board production boom, when the furniture industry recognized the advantages of this material. Low cost, easy machining, the ability to make large sheets without tree size limitations. Today, global particle board production exceeds 100 million cubic meters per year. The largest producers are China, the USA, Germany, Poland, and Russia. The boards are used everywhere: in furniture manufacturing, cabinets, tables, beds, kitchen sets, in construction, partitions, subfloors, ceiling underlayment, in packaging, pallets, crates, containers. Particleboard has some serious advantages. First up, it's incredibly efficient with wood, turning waste into a legit structural material. Second, it's cheaper than solid timber or plywood. Third, you can make sheets any size you want. You're not limited by log dimensions. Fourth, particleboard is uniform. No knots, no cracks like you'd find in natural wood. Sure, there are downsides. It hates moisture, though modern moisture-resistant boards solve that problem. It's less strong than solid wood. It contains formaldehyde, though today's E0 and E1 rated boards are practically safe. And just like that, going from a pile of wood scraps through sorting by particle size, drying at 400 degrees Fahrenheit, mixing with resin, forming a 3-layer mat, pressing under tons of pressure at 400 degrees for just a few minutes, cooling, sanding, and cutting, particleboard is born. A material that became the backbone of modern furniture manufacturing, turning waste into something valuable, saving millions of trees and making furniture affordable for billions of people across the globe. What if the most dangerous part of a suspension bridge isn't what you see? Because inside the main cables, which look like solid metal, there's a structure made of tens of thousands of wires, each one vulnerable to destruction by even a drop of salty fog. So why doesn't a bridge weighing thousands of tons collapse every single day? And what happens if moisture gets inside the cable where nobody can see it? The Golden Gate Bridge in San Francisco has 2 main cables, each about 37 inches in diameter. Inside each one, 27,572 individual wires. If you unwound all these wires and connected them into one line, you'd get roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. The weight of just one of these cables? Around 24,500 tons. That's comparable to the mass of a small cruise ship. Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made of many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of kilometers. Stay till the end. You'll learn a secret that even bridge engineers don't talk about. Picture the classic example, San Francisco's Golden Gate Bridge. It's got 2 main cables draped over towers and anchored into massive concrete blocks in the rock. Each cable's about 37 inches across. That's not a cable anymore. It's practically a pillar you'd need 2 or 3 people to wrap their arms around. Inside, 27,572 individual wires, compressed into a perfectly round bundle. Unwind all those wires and link them end to end, and you've got roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. One cable weighs around 24,500 tons, comparable to a small cruise ship or several hundred fully loaded semis. Why so many wires instead of one giant solid rod? Steel handles tension beautifully, but it doesn't tolerate flaws well, especially in large cross-sections. When a cable is made up of thousands of individual wires, each one can give a little, taking on a bigger share of the load in some spots, a smaller share in others. If one wire happens to corrode or weaken for some reason, its contribution to the overall strength is minimal, and you won't even notice it in how the whole cable behaves. Plus, it's way easier to create a flexible shape out of tens of thousands of thin elements. A cable can smoothly wrap around towers, forming a big parabola across the span, whereas a solid rod of that diameter just can't be bent without permanent deformation. The process of making the main cables for a suspension bridge is nothing like how regular steel cables are made at a factory. Nobody ships a pre-made coil a yard thick and thousands of feet long to the construction site. A monster like that would be impossible to deliver or lift into position. So the main cables of suspension bridges are spun on site. It starts with installing temporary working cables between the towers. They run a traveling cart along them that can zip back and forth across the entire span. The cart carries a coil of steel wire. Each trip of the cart means threading another wire between the shores. One end of the wire gets fixed to an anchor on one side. The cart hauls the coil across the span. The wire gets secured on the other shore, and the excess gets cut off. Then the next wire, and so on, tens of thousands of times. To keep this insane marathon from turning into chaos, the wires get organized into what are called strands or subcables. For example, several hundred parallel wires get bundled into one strand of a specific diameter. First, all the wires get tensioned with a little slack. Then special jacks even out the tension so each little wire carries roughly the same load. Then the bundle gets clamped with rings or special bands to keep it from spreading apart. When there are enough of these bundles, they get brought together and compressed again into a single cylindrical structure. A spiral wrapping of thin round wire goes on top to hold the shape, plus a protective layer of paint or other anti-corrosion coating. At this stage, the cable can already hold incredible force. Picture a bridge deck suspended from it, a steel truss or box girder carrying the road surface. This deck structure transfers the load to the main cables through suspenders. Any vehicle crossing the bridge adds several tons to the system, sometimes dozens if we're talking about a semi or multiple trucks together. Wind pushes against the side of the structure with a force that can reach thousands of kilonewtons during a storm. Ultimately, the main cables feel all of this, stretching literally just a few inches along their entire length while staying within the elastic range. The beauty of a suspension bridge is that the cable works purely in tension, not bending or compression. That's the ideal mode for high-strength steel. The modulus of elasticity and tensile strength of these cables are specifically chosen so that working stresses stay well below ultimate limits, even accounting for wind gusts, temperature swings, and heavy traffic flow. During the design phase, engineers model every possible loading scenario. Both lanes completely filled with trucks, sudden braking, seismic events. The result? An acceptable range of cable elongation and sag within which the bridge remains safe and comfortable for users. Here's the fascinating part. Despite all that rigidity, the main cables aren't absolutely static. They breathe with the bridge. On a hot sunny day, the steel expands and the cable sags slightly. At night, as temperatures drop, tension increases and sag decreases. In windy weather, you might notice a gentle oscillation in the deck. The cables themselves are actually moving too, though it's invisible to the naked eye. It's precisely this living, flexible behavior that allows suspension bridges to handle dynamic loads better than rigid, overly stone-like structures. Excessive rigidity is exactly what led to disasters in bridge building history, while controlled flexibility allows the dissipation of vibrational energy. A separate critical topic: protecting cables from corrosion. Steel fears moisture and salty fog, especially in coastal regions like San Francisco. If water and aggressive contaminants get inside a cable, reaching each of the tens of thousands of individual wires, corrosion can silently eat away the cross-section for years until it's too late. That's why immediately after strand spinning and compacting are finished, cables get sealed. First thoroughly painted, then the coating is periodically refreshed. Modern bridges employ additional systems: wrapping with airtight tapes, filling gaps with dehumidified air or nitrogen, monitoring humidity inside. Regular inspections are conducted, including magnetic or ultrasonic non-destructive testing methods, which allow engineers to understand the condition of the wires without opening up the cable. All of this is done so that a single strand of infrastructure can safely serve for decades. The cables of the Golden Gate were designed for a service life of tens of years, but thanks to proper maintenance, regular repainting, and monitoring, they still do their job today, holding up the main span of over 4,000 feet. If you add in other suspension bridges around the world, the picture becomes even more impressive. Hundreds of thousands of miles of steel wire stretched across rivers, bays, and straits, keeping millions of cars suspended in the air every single day. Using main cables made from thousands of steel wires is standard practice for large suspension bridges, so the Golden Gate isn't alone here. One of its most famous relatives is the George Washington Bridge across the Hudson in New York. It also has two main cables woven from tens of thousands of steel wires. The total length of all that wire is measured in thousands of miles, and the mass of each cable runs into tens of thousands of tons, just like the Golden Gate. The same technology was used on the Brooklyn Bridge, though it's older and combines a suspension system with cable stays. There, the main cables also consist of a large number of thin wires spun on-site rather than brought in as pre-made rope. Modern giants are built using the same principle. For example, Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made from many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of miles, and the design tension reaches hundreds of thousands of tons. A similar approach is used on numerous bridges in China and South Korea, which have been actively building long-span crossings over bays and wide rivers in recent decades. All these bridges share one technology. The main cables are spun on-site from tens of thousands of individual wires, each one tensioned, aligned, and compressed into a unified structure. This technology creates cables of incredible strength and flexibility, capable of holding thousands of tons and handling dynamic loads from wind, traffic, and temperature changes. And so, traveling from a coil of steel wire through tens of thousands of trolley trips across the void, through hydraulic jack tensioning and compression into bundles, through wrapping with protective wire and coating with anti-corrosion paint, the main cable of a suspension bridge is born, a structure of 27,572 individual wires, weighing 24,500 tons, able to stretch several inches under load but staying within elastic deformation, holding in the air a bridge over 4,000 feet long, carrying millions of vehicles every single day. Each wire is a separate element, and if one weakens, it's barely noticeable to the whole system. But if moisture and salt get inside, corrosion can silently destroy wires for years. That's exactly why modern bridges are equipped with humidity monitoring systems, regular inspections, and non-destructive testing. So these giants of steel and concrete can safely serve humanity for centuries.
Every year, the world produces billions of square feet of veneer, a petal-thin material hiding the strength and beauty of entire forests. Picture this. From a single log, you can get enough surface area to cover a football field. That's exactly why this industry is worth over $40 billion annually. From one perfect American walnut log, about 3 feet in diameter, you get anywhere from 10,000 to 30,000 square feet of unique surface. One log, almost an entire football field of veneer. Using veneer cuts the need to harvest valuable tree species by 98% compared to making furniture from solid wood. Instead of cutting down 20 trees to make 20 tables, you can harvest one perfect tree and leave the other 19 growing in the forest. But what's behind that number? How does an ordinary tree go through spa treatments, fiery tunnels, and encounters with scalpel-sharp blades to become luxury furniture? Watch closely. At the end, you'll discover a secret almost nobody realizes. Picture a lumber mill that specializes in veneer production. Massive logs of premium hardwoods, oak, ash, maple, walnut, cherry, arrive here by truck. But not every tree makes the cut. These have to be perfectly straight, tall trees with large trunk diameters, and most importantly, free of knots, cracks, and other defects for a significant height. Every knot is a scar that ruins the perfect grain pattern. That's why only the finest specimens are chosen for a veneer. When one of these perfect logs arrives at the mill, it doesn't go straight to the blade. First, it gets the industrial spa treatment. The logs are submerged in enormous pools of hot water or placed in special chambers filled with hot steam. This isn't about cleanliness. This process, lasting anywhere from several hours to several days, at temperatures around 212 degrees Fahrenheit, does two crucial things. It softens the wood, making it more pliable and cooperative for cutting, and it transforms its color, making it richer and more uniform. After the hot bath, the bark gets stripped from the log. A special machine peels away the rough outer shell, revealing clean wood underneath. And now comes the most critical moment before the main show: centering. The log gets locked into the machine, and an operator uses lasers to find its perfect axis of rotation. This is absolutely crucial. Giant pencil in a giant sharpener. The log starts spinning around its axis, and the blade cuts into the spinning wood and starts shaving off a continuous wide ribbon of veneer, just 1/50th to 1/8 of an inch thick. It's like unrolling a paper towel roll. An endless, wet, flexible sheet comes out of the machine, which is then cut into pieces of the right size. This method is highly productive, but it creates a characteristic, chaotic pattern that isn't always valued in high-end furniture. The second method, used to obtain the most beautiful decorative veneer, is called slicing. This isn't a sharpener anymore. It's the world's biggest cheese slicer. Here, a log, or part of it cut into beams, is firmly secured to a movable platform. Above it, or to the side, sits a massive, sharp blade. The platform with the wood moves back and forth or up and down, and with each pass, the blade shaves off a single perfectly flat sheet of veneer. It's a slower, less productive process, but it's what gives you that refined, linear, or figured grain pattern we value so much in expensive furniture. Depending on exactly how the log was cut before slicing, you can get different types of patterns: radial, tangential, mimicking the look of solid plank. Freshly cut veneer, no matter the method, is called green. It's soaking wet, flexible like damp paper, and tears easily. It needs to dry. The ribbons or sheets of veneer are carefully fed into a long drying chamber. Think of it as a giant tunnel oven, where the veneer slowly moves along on rollers or a mesh conveyor. Hot air circulates inside, gently and evenly pulling moisture out. The process is tightly controlled. Dry it too fast and the veneer will crack or buckle. Within minutes, that wet, floppy sheet becomes dry, slightly brittle but stable. After drying, the veneer sheets have ragged edges. They're stacked high and sent under a massive guillotine. A sharp blade slams down and in one stroke slices off the rough bits, creating perfectly straight edges. Now the sheets are ready for the most critical stage, where it's not machines doing the work, it's people with trained eyes. This is sorting. Specialists carefully inspect each sheet, evaluating its color, grain pattern, and any defects, then sort them into bundles by grade. It's meticulous work because this determines the veneer's price and application. But individual veneer sheets are often too narrow for making something like a tabletop, so they need to be joined into one large panel. This process is called stitching or splicing. Two sheets with perfectly straight edges are fed into a special machine. It presses them tightly together, and a specialized mechanism bonds them. This could be a thin zigzag line of adhesive or a glued paper tape. The result? A large, continuous veneer sheet, ready to be applied to a substrate. Now for some history. Using thin layers of wood goes back thousands of years. Ancient Egyptians used veneer to decorate sarcophagi and furniture 3,000 years ago. But modern industrial veneer production only began in the 19th century with the invention of steam engines and precision machinery. The first veneer peeling lathes appeared in the mid-19th century and revolutionized the furniture industry. Instead of sawing valuable wood species into thick boards and losing most of the material to sawdust, manufacturers could now obtain ultra-thin sheets, maximizing every inch of the log. The global veneer market is a massive industry, turning over more than $40 billion a year. The largest producers are China, the US, Germany, Italy, and Indonesia. Veneer isn't just for furniture. It's used in making doors, musical instruments, yacht interiors, luxury car interiors, and premium space finishes. But the most important application is plywood. Yes, ordinary plywood as we know it is multiple layers of veneer glued together with perpendicular grain direction. This exact structure gives plywood its strength and resistance to warping. And now the most impressive number behind veneer, its efficiency rating. Take one massive, perfectly straight log of premium American walnut, several yards long and about 3 feet across. If you just sawed it into boards, you could make, say, one big table and a few chairs. Now here's the kicker. If you slice that same log into veneer just 24 thousandths of an inch thick, you can get anywhere from 10,000 to 30,000 square feet of unique surface. To put that in perspective, that's enough to cover almost an entire football field from a single log. Using veneer cuts the need to harvest precious hardwoods by 98% compared to making solid wood furniture. Meaning instead of cutting down 20 trees to build 20 tables, we can harvest one perfect tree and leave the other 19 growing in the forest. This makes veneer one of the most environmentally responsible ways to use wood. But veneer has another hidden advantage that few people think about. The thing is, the most beautiful, unique wood grain patterns are often found in the most unusual parts of a tree, where the trunk branches out, in burls, in the root section. If you saw a tree like that into boards, these areas often end up as scrap because they're too small or irregularly shaped. But with veneer production, even a small section with a unique pattern can be turned into several square meters of luxurious material. There are entire categories of exclusive veneer made from burls, wood growths with incredibly complex, swirling patterns. One burl the size of a soccer ball can yield enough veneer to finish an entire study, and this veneer can cost thousands of dollars per square meter. There's even a market for archive veneer, material made from trees cut down decades or even centuries ago and stored in warehouses. Some species of wood that are now protected or extinct can only be found in the form of this archive veneer. Veneer manufacturing technology is constantly evolving. Modern machines are equipped with laser scanning systems that analyze the log structure before cutting and select the optimal angle and method to produce the most beautiful grain pattern. Computer control allows sheets less than half a millimeter thick to be sliced with precision down to hundredths of an inch. New processing methods are being developed that enable veneer to be stained, embossed with textures, and made to imitate rare species. And so, after journeying from a majestic tree in the forest through a hot bath at 200 degrees Fahrenheit, past a knife sharp as a scalpel, and through the fiery tunnel of a dryer, this material emerges, thin as a petal, carrying all the beauty, history, and unique character of the forest, ready to bring a piece of it into our homes. These billions of dollars aren't just money, they're proof that beauty and practicality can walk hand in hand, allowing us to enjoy nature's unique patterns without causing irreparable harm. Every sheet of veneer is a thin slice of a tree's history, one that lived for decades or centuries and is now ready to serve humanity for centuries more in the form of beautiful furniture. What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, then gets reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore flare up like tiny controlled earthquakes. Zinc, the fourth most consumed metal in the world after iron, aluminum, and copper. 12 to 13 million tons of zinc are produced every year. 60% of all zinc goes into galvanizing steel. Without it, bridges, cars, and buildings would rust many times faster. But here's the shocker. At 2700 degrees Fahrenheit, zinc literally turns into vapor and disappears into the air, and then condenses back into liquid metal. In this video, you'll learn things you never suspected, and at the end, the main secret will be revealed that will forever change how you think about zinc. Picture a massive underground mine somewhere in China, Australia, or Peru, the world's biggest zinc producers. These are entire underground cities stretching hundreds of feet, sometimes even miles beneath the Earth's surface. We're not talking about simple holes in the ground. This is a network of tunnels, shafts, ventilation systems, and lift shafts. Powerful drilling rigs bore holes into the rock, blast holes. Explosives get packed into these holes. After a carefully controlled blast, massive volumes of rock break apart. It's like a spectacular but controlled earthquake in miniature. Dusty air gets quickly cleared by powerful ventilation systems, which also pump fresh air down to these depths. The broken ore then gets loaded onto massive underground trucks or conveyor belts using front-end loaders. It's a genuine underground transportation flow, continuously moving, hauling tons of ore to the central lift shafts. From there, the ore rises to the surface using powerful elevators or specialized conveyor systems, climbing hundreds of feet straight up. At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock, containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a concentrator plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore into crushers that, with a deafening roar, break them down into smaller pieces. Then this crushed ore moves into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore is ground down to an extremely fine powder, almost like flour. This is critically important to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder is mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. The zinc mineral particles latch onto these bubbles and rise to the surface, forming foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can contain up to 60% zinc. Since zinc is often found alongside lead, the processing plant may run multiple flotation cycles to separately extract zinc concentrate from lead concentrate. The zinc concentrate you end up with still isn't pure metal. It has to go through metallurgical processing to get metallic zinc. And now we enter the world of extreme temperatures. If the pyrometallurgical method is used, the zinc concentrate first undergoes roasting. The concentrate is heated in specialized furnaces at temperatures around 1800 degrees Fahrenheit. This removes the sulfur, which is part of the sulfide ore, converting it into zinc oxide. The sulfur transforms into sulfur dioxide gas, which is captured and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable product. Next, the zinc oxide is mixed with coal and heated to even higher temperatures, over 2200 degrees Fahrenheit, sometimes even 2700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process occurs. The carbon strips oxygen away from the zinc oxide, freeing up pure metallic zinc. And this is where that incredible wow moment of vaporization happens. At these temperatures, the metallic zinc transitions into a gaseous state. It evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is significantly higher, zinc literally turns into vapor, which rises and gets collected in specialized condensers. The vapor cools and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or granules. Now for the history. Zinc has been known to humanity for thousands of years, though it was only isolated as a distinct metal in the 16th century. Ancient civilizations used brass, an alloy of copper and zinc, without knowing it actually contains zinc. In India and China, people learned to smelt zinc as far back as the Middle Ages. But modern industrial zinc production only began in the 19th century with advances in smelting technology. The primary use of zinc: galvanizing steel. Around 60% of all zinc produced goes toward protecting steel from corrosion. Zinc coating on steel creates a sacrificial layer. The zinc oxidizes instead of the iron, protecting the structure. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a surge in resource demand. "15 to 20% of zinc goes into making alloys like brass and die-casting alloys. These alloys end up in car parts, home appliances, toys, plumbing, and electronics. Another 10 to 15% becomes zinc oxide and other chemical compounds. Zinc oxide has crazy wide applications: sunscreens and cosmetics, paints, ceramics, rubber manufacturing, and even livestock feed supplements. Its antibacterial and protective properties make it a universal ingredient. The rest of the zinc gets used in batteries, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, because zinc is absolutely vital for the human immune system. As for prices, like most commodities, zinc prices swing with global supply and demand, economic cycles, and what's happening in the biggest producer and consumer countries. Yet demand for zinc remains steady or growing, driven by urbanization, infrastructure development, and the need to protect metals from corrosion worldwide. This makes zinc a crucial indicator of global economic health. Zinc ranks as the fourth most consumed metal on the planet, after iron, aluminum, and copper. That alone tells you just how massive its importance is for the global economy and industry. Annual worldwide zinc production sits at roughly 12 to 13 million metric tons. These are enormous volumes, underscoring its irreplaceability across hundreds of applications. The primary zinc mining regions are China, Australia, and Peru. These three countries together account for a significant share of global zinc ore extraction, making them key players in the market. For instance, China isn't just the largest producer, it's also the world's biggest zinc consumer, reflecting its powerful industrial expansion. Other major producers include India, the United States, Mexico, and Canada. When it comes to reserves, the U.S. Geological Survey estimates global zinc reserves at roughly 250 million metric tons. On top of that, there are what's called resource spaces, potential deposits that haven't been explored yet or aren't economically viable to mine right now. Those are estimated at over 1,800 million tons. These numbers show that zinc, unlike some rare metals, will last for many decades, even with growing consumption. Most zinc is mined from underground operations, entire subterranean cities stretching hundreds of feet, sometimes several miles beneath the Earth's surface. These aren't just holes in the ground, They're networks of tunnels, shafts, ventilation systems, and hoisting shafts. It all starts with exploration. Geologists, like detectives, hunt for ore bodies, sections of rock where the concentration of zinc, which, by the way, usually occurs as sulfide ore, like sphalerite, and almost always comes with lead, silver, and sometimes copper, is high enough to make it worthwhile. Once a deposit is discovered, mine construction begins. This involves sinking vertical shafts, which provide access to the ore, lift materials up, lower equipment down, and creating horizontal tunnels, or drifts, that lead directly to the ore veins. The actual ore extraction process? Dynamic, risky. Miners use specialized equipment, powerful drilling rigs that bore holes into the rock, called blast holes. Explosives get packed into these holes. After a carefully controlled detonation, massive volumes of rock shatter. It's like a spectacular earthquake, in miniature, under control. And that's how, starting from an underground explosion, through crushing into powder, through flotation with millions of tiny bubbles, through roasting at 1800 degrees and reduction at 2700 degrees, where the metal literally turns into vapor and vanishes into thin air, then condenses back into liquid zinc, a metal is born that shields steel from rust, makes bridges possible, cars, skyscrapers, without which the modern world would look completely different.
Picture this. Glass that once shattered into deadly shards now saves lives. How did humanity transform a fragile substance into armor for your car? Every year, the world produces over 100 million square meters of automotive glass, enough to cover an entire country. But the real magic happens where molten rock becomes a perfectly smooth surface, in furnaces reaching temperatures over 2,700 degrees Fahrenheit. That's hotter than the surface of molten lava. How did ordinary quartz sand become the foundation of a safety technology we can't imagine modern transportation without? What accidental experiment changed the history of automobiles forever? You'll discover how the first safety glass was created, what secrets hide within its layers, and why modern windshields can withstand the impact of a rock at 60 miles per hour. Watch until the end. The finale reveals how many stages glass goes through to protect your life. The history of automotive glass production is closely tied to the development of the automobile industry, which emerged in the late 19th century. When the first cars began appearing on roads, they weren't equipped with glass at all. The open body design only partially protected passengers, while dust, wind, insects, and other hazards made trips extremely uncomfortable. Later, as cars got faster, the need arose to install protection for drivers and passengers. Windshields started being made from ordinary window glass, which, while providing some protection, had a serious flaw. During accidents, it shattered into large, sharp shards, leading to numerous injuries and deaths. Glass sliced faces, necks, arms of drivers and passengers. This was a real problem demanding an urgent solution. The first revolutionary breakthrough in automotive glass came with the creation of laminated glass, and it happened by accident. In 1903, French chemist Edouard Benedictus accidentally knocked over a flask coated with nitrocellulose. The glass cracked, but stayed intact thanks to a thin plastic layer. This accident inspired the scientists to create multi-layer glass, which later became the foundation for laminated safety glass. By the 1910s, laminated glass started appearing in premium automobiles. Its construction consisted of two glass layers with a thin, transparent film sandwiched between them. On impact, the glass wouldn't shatter. Cracks would stay trapped in the film. In the 1920s, laminated glass became widely used in windshield production. Its main advantage? Enhanced safety. Even in serious crashes, fragments wouldn't fly everywhere. They'd stay locked in the polymer layer. The next stage in automotive glass development came in the 30s. when tempered glass manufacturing technology was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it shattered, it broke into small pieces with blunt edges, minimizing injuries. In the mid-20th century, tempered glass began to be used for side and rear car windows. It was cheaper to produce compared to laminated glass and provided a sufficient level of safety for these parts of the vehicle. In the 50s and 60s, automotive glass became even more advanced thanks to technological developments. Important changes occurred: improvements to laminated glass, and the development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production and automation of manufacturing processes allowed for a reduction in the cost of automotive glass. One of the biggest technological breakthroughs in glassmaking came in 1959 with the invention of the float process. This technology, developed by British company Pilkington, made it possible to manufacture perfectly smooth glass by spreading molten glass across a surface of molten tin. Picture this. Red-hot liquid glass pours onto a mirror-like surface of molten metal and spreads itself out, forming a perfectly flat sheet. Thanks to this method, glass became more uniform, stronger, and accessible for mass production. The float process is still the foundation of automotive glass manufacturing today, ensuring precise dimensions, smooth surfaces, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 60s, heating wires started being installed in rear windows to prevent fogging and freezing. In the 80s, glass with special metallic coatings appeared that reflected sunlight and reduced cabin heating. UV protective glass, thanks to new technologies, began providing nearly complete protection from harmful radiation. Modern automotive glass is divided into several types depending on its purpose and manufacturing technology. The windshield is typically laminated glass consisting of 2 layers of glass with a polymer film sandwiched between them. This design ensures that when damaged, the glass doesn't shatter into sharp fragments. Side and rear glass are most often tempered glass, which breaks into small blunt pieces upon impact, reducing injury risk. Panoramic roofs or other specialty glass types often use laminated or tempered glass with special coatings for ultraviolet radiation protection. The main components of glass are natural materials mixed in specific proportions to achieve the desired properties. Quartz sand is the primary ingredient of glass, providing its transparency. It must be extremely pure with minimal impurities. Soda is added to lower the melting point of glass. Lime improves the mechanical strength and chemical properties of glass. Additional additives are used to adjust color, transparency, resistance to ultraviolet light, and other characteristics. The raw materials are purified, dried, and ground to a uniform consistency. It's critical that impurities that could affect glass quality are eliminated as much as possible. After the raw materials are prepared, they're loaded into specialized furnaces for melting. The melting temperature to form glass reaches around 5,000 degrees Fahrenheit. This is the temperature at which stone transforms into liquid. During the melting process, the raw materials become a uniform, viscous fluid. The glass mixture gets stirred to distribute components evenly. This matters. You want to avoid air bubbles or inconsistencies in the finished product. Glass melting furnaces come equipped with modern temperature control systems and process automation, ensuring top quality end results. After melting, the glass mass undergoes forming, which in modern production is most often done using the float process. Liquid glass flows out of the furnace and enters a bath of molten tin. Thanks to tin's high density, the glass mass spreads evenly across its surface. Under its own weight, the glass forms a perfectly flat and smooth surface. Gradually lowering the temperature, the glass hardens. By the time it exits the bath, it's ready for processing. The float method allows manufacturers to produce glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions needed for automotive production. Automated cutting machines ensure precision in the process. To prevent cracks and chips, the glass edges are ground down. Each sheet undergoes inspection for defects like microcracks, bubbles, or other damage. To guarantee the strength and safety of automotive glass, it goes through a tempering process. The glass is heated to around 1,112 degrees Fahrenheit. Then the glass surface is rapidly cooled by air jets, while the inner layers cool more slowly. This creates tension that increases impact resistance. When tempered glass breaks, it shatters into small, safe fragments, minimizing the risk of injury. Windshields use laminated glass, a construction of glass and polymer film. Its manufacturing involves several steps. A polymer film is placed between two glass sheets. The construction is put into a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure. This creates a rock-solid bond between the layers. Laminated glass has exceptional impact resistance, and when damaged, it stays held together by the polymer film, keeping drivers and passengers safe. To enhance automotive glass properties, various coatings are applied. Anti-glare coatings reduce reflections from the sun or headlights of other cars. UV protection, special layers block harmful ultraviolet radiation. Hydrophobic coatings make water sheet right off the glass surface. Heating elements, thin heating wires can be embedded in the windshield, making it easier to clear ice or fog. To achieve the exact shape needed, special thermoforming equipment is used. The glass is heated to a temperature where it becomes pliable and is formed according to the specified parameters. In the final stage, every piece undergoes rigorous inspection. They check for clarity and defects. The glass is tested for impact resistance and load endurance. Standards compliance, dimensional accuracy, shape, and other parameters are verified. The finished automotive glass is packaged to prevent damage during transport. It's shipped to auto plants or service centers where it's installed in vehicles. And that's how, journeying from quartz sand through the hellish flames of furnaces at 5,000 degrees Fahrenheit, through a bath of molten tin, through tempering and lamination, glass is born, capable of protecting life at 75 miles per hour. This is the story of how an accidentally shattered flask changed the automotive world forever. Automotive glass production is a high-tech process combining physics, chemistry, and engineering. Thanks to modern technology and strict quality control standards, automotive glass delivers safety, comfort, and durability. Every time you get in a car, remember, between you and danger, a thin layer of glass that's passed through dozens of production stages to save your life in that critical moment.
The metal hiding in every muffler. Every minute, 130 cars roll off production lines around the world, and each one hides between 2 and 7 grams of palladium, a metal more expensive than gold and platinum, so rare that all the world's reserves could fit in a single room. But without it, every modern city would choke. Palladium scrubs poisonous substances from exhaust gases. 85% of all palladium mined goes into automotive catalysts. Platinum's little brother has become the critically important metal of the 21st century. How do you extract a silvery metal worth $40,000 per kilogram from ore mined a kilometer underground in Siberia? You'll learn why palladium was named after an asteroid, how it transforms poison into harmless gas, and why its reserves could run out in 20 years. Watch until the end. The finale reveals what stands behind the clean air in our cities. This is the story of the metal the future of the automotive industry depends on. The story of palladium began in 1803 in London. British chemist William Wollaston was studying platinum ore from South America. He dissolved the ore in aqua regia, a mix of hydrochloric and nitric acids, the only solvent capable of dissolving platinum. From the solution, he extracted platinum, but noticed some impurities remained in the solution. Wollaston performed a series of chemical operations and isolated a new metal, silvery white, similar to platinum, but lighter. He named it palladium after the asteroid Pallas, discovered a year earlier. Coincidence or not, Pallas in Greek mythology is the goddess of wisdom. Palladium turned out to be an amazing metal. It could absorb hydrogen in volumes 900 times its own. Picture this. A cube of palladium 1 centimeter by 1 centimeter can soak up nearly a liter of hydrogen. The metal swells up like a sponge. But the key property was discovered later: catalytic activity. Palladium speeds up chemical reactions without taking part in them. For a long time, palladium remained a laboratory curiosity. It was used in jewelry. White gold often contains palladium. In dentistry, for dental crowns. In electronics, palladium contacts don't oxidize, but consumption was minimal, just a few tons a year for the entire world. Everything changed in the 1970s, when environmental regulations suddenly got much stricter. Car exhaust contains carbon monoxide, nitrogen oxides, and unburned hydrocarbons, all of them toxins. Cities were choking in smog. A solution was needed, and one was found: the catalytic converter, a device that transforms poisonous gases into harmless ones. Inside a stainless steel casing, a ceramic honeycomb structure coated with an ultra-thin layer of platinum, palladium, and rhodium. Hot exhaust gases pass through the honeycomb. On the surface of the platinum group metals, reactions occur. Carbon monoxide converts to carbon dioxide, nitrogen oxides to harmless nitrogen, hydrocarbons burn off. The converter cuts emissions by 95%. But there's a price. Each converter contains precious metals.
Palladium turned out to be perfect for the job. It's cheaper than platinum, but better at oxidizing hydrocarbons. With environmental regulations rolling out in Europe and the US, demand for palladium exploded. Production jumped from just a few tons a year to 300 tons. The price rocketed from $500 per troy ounce in the 90s to $3,000 in 2020. Palladium became more expensive than gold and platinum. Catalytic converter thefts started spreading. Thieves cut the converter out from under a car in 5 minutes and sell it for $200 to $500. The palladium inside is worth even more. The problem is, palladium is one of the rarest elements out there. In the Earth's crust, it makes up 6 parts per 10 billion. That's 30 times rarer than gold. Worldwide, only about 200 tons of palladium get mined each year. For comparison, 3,000 tons of gold, 20 million tons of copper. Palladium doesn't form its own deposits. It shows up as an impurity in nickel and platinum ores. Main sources: Russia and South Africa. 70% of the world's palladium comes from Russia, mostly from the Norilsk mining complex in Siberia. Norilsk is a city above the Arctic Circle, one of the most northern cities on the planet. Winter temperatures drop to -50. But underground lies a unique deposit of copper-nickel ores containing platinum group metals. The ore is mined in shafts up to nearly a mile deep. They blast the rock, load it onto dump trucks, bring it to the surface. The ore contains about 1% nickel, fractions of a percent copper, and just a few grams per ton of platinum group metals: platinum, palladium, rhodium, iridium. But the volumes are massive. 20 million tons of ore per year. The ore is crushed, ground into fine powder, enriched by flotation. The process is similar to lead ore enrichment. They get a concentrate containing 10 to 15% nickel and copper and elevated levels of precious metals. The concentrate is smelted in massive furnaces. This produces matte, an alloy of nickel, copper, and iron sulfides. All the platinum group metals are concentrated in the matte. Feinstein gets shipped to a metallurgical plant. There, it's converted, blasted with oxygen at temperatures hitting 1,200 degrees.
iron and sulfur oxidize and get stripped away. What you're left with is crude nickel-copper alloy containing the platinum group metals. This alloy gets dissolved in sulfuric acid. Nickel and copper go into solution. Precious metals stay behind in the residue, what they call slimes. These slimes contain up to several percent platinum group metals. It's not palladium yet, but it's highly concentrated feedstock. The slimes get dissolved in aqua regia, that same acid mixture Wollaston used. All the platinum group metals go into solution. Now the ultra-precise separation chemistry begins. From the solution, they sequentially precipitate platinum, palladium, rhodium, iridium, ruthenium, osmium. Each metal precipitates at a specific pH with specific reagents. The process takes weeks. The result, precipitates of various palladium salts. These salts get calcined at high temperature. You get sponge palladium, a gray porous powder. It's almost pure metal, but not yet a marketable product. Spongy palladium gets melted down in an induction furnace under argon or vacuum. Palladium can't oxidize. The molten metal pours into ingots. You end up with small bars weighing anywhere from a few ounces to 2 pounds. Silvery white with a slight steel tint. Palladium's softer than platinum, so you can roll it, forge it, draw it into wire. Palladium's melting point? 2,828 degrees Fahrenheit, lower than platinum. Density? About 0.43 pounds per cubic inch, lighter than platinum, but still a seriously heavy metal. Palladium doesn't tarnish in air, doesn't react with most acids, only dissolves in aqua regia and hot concentrated nitric acid, corrosion resistant. But here's the key property, catalytic activity. Palladium speeds up oxidation and reduction reactions. On its surface, gas molecules get adsorbed, activated, react with each other. That's exactly what makes palladium irreplaceable in automotive catalytic converters. The entire journey from ore to metal takes months and involves dozens of processing steps. How does a palladium car catalytic converter work? The device looks like a metal canister installed in the exhaust system right after the engine. Inside is a ceramic honeycomb structure, like an actual beehive. Thousands of channels in this structure. Total surface area, several square feet. The surface is coated with aluminum oxide, a thin porous layer that multiplies the area hundreds of times over. On top of that layer, palladium, platinum, and rhodium, total weight between 2 and 7 grams. Palladium and platinum oxidize carbon monoxide and hydrocarbons into carbon dioxide and water. Rhodium reduces nitrogen oxides back to nitrogen. Exhaust gases at temperatures between 750 and 1470 degrees Fahrenheit flow through the honeycomb. Reactions happen on the metal surfaces. What comes out? Almost pure nitrogen, carbon dioxide, and water vapor. Efficiency? Up to 98%. Without a catalytic converter, a car dumps dozens of grams of toxins into the atmosphere every mile. With one, fractions of a gram. A modern passenger car contains 3 to 5 grams of palladium. A truck or SUV, up to 7 grams. Here's the problem. Palladium reserves are limited and running out. There aren't many accessible deposits left. At current extraction rates, proven reserves will last 20 to 30 years. Prices are climbing. The shortage is getting worse. Automakers are hunting for alternatives to palladium. They're partially switching to platinum. It's also a catalyst, but more expensive and less effective for gasoline engines. For diesels, platinum works better. Recycling palladium from spent catalytic converters is ramping up. Old converters get collected, crushed, and the platinum group metals extracted. Recycling provides up to 30% of palladium supply. It helps, but it doesn't fully solve the problem. Demand keeps growing. Around 90 million cars roll off production lines worldwide every year. Electric vehicles don't use catalytic converters, but their share of the market is still small. Hybrids still need palladium. The palladium market's unstable. Prices swing from $2,000 to $3,000 per troy ounce. Palladium has become a strategic metal. The entire automotive industry and urban air quality depend on it. And just like that, journeying from ore a mile deep beneath the Siberian permafrost, through months of chemical operations and ultra-precise separation, palladium emerges into the world, platinum's younger brother, now the champion of clean air. A few grams of silvery metal hidden inside every muffler, saving millions of lives annually. The rarest of elements, 30 times scarcer on Earth than gold, has become critically vital to modern civilization. It's the paradox of technological progress. The more we care about ecology, the more we depend on rare metals. Every time you start your car, remember, beneath the chassis works a palladium catalyst, transforming poisons into harmless gases. A metal worth $40,000 per kilogram makes city air breathable. From the asteroid palace to automotive catalysts, 220 years of history for a metal that found its calling in the fight for ecology. But reserves are dwindling, prices are climbing, and palladium's future looks uncertain. Perhaps in 20 years, humanity will discover a replacement, or learn to recycle more efficiently, or switch to electric vehicles. But for now, palladium remains the thin, silvery thread connecting a billion automobiles to clean air, the metal without which megacities would suffocate, the hidden hero of the environmental revolution, tucked away in every muffler.
A poisonous metal that saves lives. Sounds paradoxical, but it's true. Lead, one of the most toxic elements on Earth. It poisoned Roman emperors, killed thousands of workers, got banned from paint and gasoline. But without it, not a single car on the planet would start. Every second, the world produces 2 tons of lead. 85% goes into batteries, the heart of every vehicle. Lead shields doctors from X-rays and stops radiation at nuclear plants. The heaviest common metal you can hold in your hands, 11 grams per cubic centimeter. How do you get a bluish metal that kills and saves at the same time from silver ore? You'll find out why the Roman Empire fell because of lead pipes, how a lead-acid battery works, and why this ancient poison is still irreplaceable today. Watch till the end. The finale reveals the dark side of progress. This is the story of a metal humanity can neither embrace nor let go. Lead's story begins deep in ancient times. About 7,000 years ago, people learned to smelt lead from ore. It was one of the first metals humans extracted from stone. Lead melts at a low temperature, just 627 degrees Fahrenheit. Even a campfire can melt lead ore. The ancient Egyptians used lead to make statuettes and cosmetics. Yes, women lined their eyes with lead-based white paint. The Roman Empire took lead use to absurd levels. Lead water pipes stretched throughout Rome. Wine was stored in lead amphorae. The metal made the drink sweeter. Wealthy Romans ate from lead dishes. Aristocracy sweetened wine with lead sugar, lead acetate, which actually tastes sweet. The result? Mass poisonings. Roman nobility suffered from gout, insanity, infertility. Many historians believe lead poisoning of the elite became one of the causes of Rome's fall. Emperor Nero, known for his madness, may have been poisoned by lead since childhood. In the Middle Ages, lead was used to make cathedral roofs, stained glass windows, and printing type. Alchemists considered lead the basest of metals and tried to turn it into gold. The 19th century brought a boom in the lead industry. Lead white became the foundation for paints, bright, durable, cheap. Lead coated toys, furniture, house walls. Children gnawed on lead toys and died from poisoning. Workers at lead plants perished by the dozens. Metal dust destroyed their nervous systems. In the 20th century, lead was added to gasoline as an anti-knock additive. Tetraethyl lead boosted octane ratings. Engines ran smoother. But exhaust fumes poisoned cities. By century's end, leaded gasoline was banned almost everywhere. Lead paints were banned too. Lead pipes replaced with plastic. It seemed the age of lead was over. But no. Lead production kept growing because a new massive application emerged: car batteries. Where does lead come from today? The primary lead mineral is galena, lead sulfide, cube-shaped crystals, silvery gray with a metallic luster, extremely heavy, density of about 0.27 pounds per cubic inch. Galena often occurs alongside silver, zinc, copper. The largest deposits are found in China, Australia, the USA, Peru, Mexico. China produces half the world's lead, around 6 million tons per year. Lead is extracted through open-pit mining in quarries or underground mines. They blast the rock, crush it, grind it. The result is ore containing 3 to 10% lead. That's enough for industrial processing. The ore is enriched through flotation. Crushed ore is mixed with water and special reagents. Galena particles stick to air bubbles and float up, forming foam. Waste rock gets washed away. The concentrate contains up to 70.
Lead concentrate gets roasted in massive furnaces at around 1800 degrees Fahrenheit. Lead sulfide transforms into lead oxide, releasing sulfur dioxide gas. They capture this gas and use it to make sulfuric acid. Nothing goes to waste. Lead oxide gets mixed with coke and fluxes, limestone or quartz. Loaded into a shaft furnace. Hot air blasts in from below. Temperature climbs to 2200 degrees. Carbon reduces the lead oxide back to metal. Molten lead pools at the bottom of the furnace, a heavy gray-blue liquid. Lead is 11 times denser than water. Drop a steel ball into molten lead and it'll float right on the surface. They tap the melt from the furnace into ladles. The melt's still impure, contains copper, zinc, silver, gold. Yeah, lead ore often carries precious metals. Extracting them pays for part of production. Lead gets refined, purified. Heat it to 900 degrees and add zinc. Silver and gold dissolve in the zinc and float up. They skim them off.
The purified lead gets poured into ingots. A standard ingot weighs about 55 pounds and is the size of a brick, but it weighs like a bag of cement. Try lifting it. Lead is heavy and soft. You can cut it with a knife, scratch it with your fingernail. At room temperature, lead develops a dull oxide film, loses its shine. A fresh cut is silvery blue, beautiful, but goes dull within a minute. Lead doesn't rust in the usual sense. The oxide film protects the metal from further corrosion. That's why Roman lead pipes have survived 2,000 years. But the key property of lead is its toxicity. Lead and its compounds are poisonous. Once it enters the body, lead accumulates in bones, replacing calcium. It destroys the nervous system, causes anemia, damages kidneys and brain. Especially dangerous for children. Even tiny doses disrupt nervous system development. There is no safe level of lead in blood. Any amount is harmful. That's why working with lead demands the strictest safety measures: respirators, protective clothing, showers after every shift.
But if lead is so toxic, why do they keep producing it in such massive quantities? Because lead has properties that simply can't be replaced. First, its weight. Lead is 1.5 times heavier than iron. Second, it's soft and easy to work with. Third, it blocks radiation. Gamma rays and X-rays are absorbed by lead better than any other affordable metal. Only gold and tungsten are better, but they're way too expensive. So lead gets used for radiation protection. X-ray room walls are lined with lead sheets. Doctors and technicians wear lead aprons, weigh about 10 pounds, uncomfortable, but they protect. Containers for transporting radioactive materials are made from lead several inches thick. At nuclear power plants, lead is used in shielding systems. Viewing windows for observing reactors are made from leaded glass, transparent, but contains up to 70% lead oxide. This glass stops radiation while letting light through. Without lead, nuclear medicine and power wouldn't be possible.
But the main use of lead? Batteries. 85% of global lead production goes into lead-acid batteries. These are the most common type of battery on the planet. Every car with an internal combustion engine has one. 1 billion cars means 1 billion lead batteries. How does it work? Inside a plastic case, there are plates made of lead and lead dioxide submerged in sulfuric acid. During discharge, the lead and lead dioxide react with the acid, forming lead sulfate and water. Electrical energy is released. During charging, the process reverses. Electricity converts the lead sulfate back into metal and dioxide. This cycle can repeat hundreds of times. Lead-acid batteries are reliable, cheap, and can handle high currents. Perfect for starting an engine. A starter motor draws hundreds of amps. Lithium-ion batteries can't compete in this application yet. One car battery contains between 22 and 33 pounds of lead. It lasts 3 to 5 years, then gets recycled. Lead is the recycling champion among all materials. Up to 99% of lead from old batteries makes it back into production. An old battery gets dropped off at a collection point where it's disassembled and crushed. Lead plates are melted down, purified, and cast into ingots. A new battery contains up to 80% recycled lead. This makes economic sense. Secondary lead costs less than primary. And it's environmentally sound. No need to dig new mines. Global lead production runs about 12 million tons per year. Roughly half comes from recycled material. Lead prices hover around $2,000 per ton, cheap compared to other metals. Beyond batteries and radiation shielding, lead shows up in cable sheathing, ammunition, fishing weights, and wheel balancing weights, in construction for soundproofing and waterproofing. But these uses are gradually declining as manufacturers hunt for less toxic alternatives. Lead's future lies in batteries and radiation protection. Until someone invents a replacement, lead remains irreplaceable.
And just like that, traveling from silvery galena crystals through the inferno of furnaces at 1200 degrees and complex purification from impurities, lead emerges, the most contradictory metal in human history. A metal that poisoned Roman emperors and saves lives in hospitals. Banned in paints and toys, yet no car starts without it. Heavy, soft, toxic, but irreplaceable. This is the story of progress's dark side, how a poisonous element became the foundation of modern civilization. Every time you turn your ignition key, get an X-ray, or have a chest scan, know this: lead is working for you, shielding you from radiation, storing energy, starting engines. The paradox of a metal that kills when mishandled and saves when used right. 7,000 years alongside humanity, from ancient figurines to modern batteries. Lead is a reminder that progress always has a price, and that price is sometimes written on the periodic table with the symbol Pb, plumbum, from the Latin word meaning heaviness, the weight of choosing between toxicity and necessity. A metal humanity cannot abandon, no matter how hard it tries.
Picture this: 8% of all CO2 on the planet comes from one industry, steel. Every single second, the world produces 60 tons of steel, and every ton leaves behind nearly 2 tons of carbon dioxide. But in Sweden, something seemingly impossible happened. They made steel without coal, 0 coal. Instead, hydrogen and electricity. Sounds like science fiction? In 2021, a Volvo truck built from this steel hit the roads. The first vehicle in history made from steel with a 0 carbon footprint. How is humanity walking away from a technology that's 3,000 years old? You'll learn why traditional steelmaking is killing the planet, how hydrogen is replacing coal and blast furnaces, and why this revolution will change everything, from skyscrapers to cars. Watch to the end. The finale will show you that the future of steel isn't black anymore. It's green.
The history of steel production began 3,000 years ago when humanity learned to smelt iron. The principle remained unchanged for millennia. Iron ore is heated with coal. Carbon strips oxygen from iron oxide, and you get pure iron. This is called reduction. And the byproduct? Carbon dioxide, which escapes into the atmosphere. For centuries, nobody cared. In the 19th century, blast furnaces appeared, steel giants as tall as a 20-story building. Inside, temperatures hit 3,600 degrees Fahrenheit. Superheated air blasts in from below, while iron ore and coke, specially fired coal, get loaded from above. The ore descends, meets the carbon, and out comes molten pig iron, glowing orange like lava. Pig iron then becomes steel by blowing oxygen through it to remove excess carbon. This technology fueled the Industrial Revolution, built skyscrapers, bridges, ships, automobiles, but it comes with a monstrous cost. Every ton of steel requires about 1,300 pounds of coke. When burned and used to reduce the ore, it produces nearly 4,000 pounds of carbon dioxide for every ton of steel. Global steel production, almost 2 billion tons per year. Do the math, around 7.5 billion tons of CO2 annually. That's 8% of all global greenhouse gas emissions, more than all aviation worldwide. If the steel industry were a country, it would rank third in emissions after China and the US. And the problem's getting worse. Demand for steel is rising, especially in developing countries. By 2050, emissions from steelmaking could double if nothing changes. Humanity's caught in a trap. Modern civilization is impossible without steel, but steel is killing the climate. Aluminum or plastic can't replace steel in most applications. The properties are just too different. We needed a revolution, and it started in cold Sweden, in the city of Luleå, above the Arctic Circle. In 2016, 3 Swedish companies, SSAB, Vattenfall, and LKAB, announced the launch of the Hybrid project, Hydrogen Breakthrough Iron-Making Technology, a breakthrough technology for producing iron with hydrogen. The idea seemed insane. Replace carbon with hydrogen in the ore reduction process. Instead of the iron plus carbon reaction that produces CO2, use iron plus hydrogen, which gives you H2O, water, just water, no carbon dioxide. But the challenge was titanic. They needed to build a hydrogen production plant using electrolysis, powered by renewable energy. They needed to design direct reduction reactors that use hydrogen to process iron. They needed to prove this iron could be transformed into quality steel and make all of it economically viable. 5 years of work, hundreds of millions of euros in investment. In June 2021, they fired up the world's first hydrogen-based steel plant in Luleå, a pilot facility, but fully operational. The revolution had begun. Now let's break down how this actually works. The process starts with hydrogen production. Typically, hydrogen comes from natural gas, but that creates CO2 emissions. Hybrid uses water electrolysis. They run electric current from wind and hydroelectric plants through water. The water splits into hydrogen and oxygen, pure green hydrogen, 0 emissions. This hydrogen feeds into a shaft furnace, a direct reduction reactor. Iron ore pellets get loaded from the top. These are walnut-sized granules made of iron oxide. Superheated hydrogen enters from below at around 1,500 degrees Fahrenheit. The hydrogen rises up through the pellet bed. A chemical reaction occurs. Hydrogen strips the oxygen from the iron oxide. What forms is metallic iron and water vapor. Yep, just steam. The pellets sink downward, gradually losing oxygen and transforming into porous iron, called sponge iron or direct reduced iron, DRI. What comes out are gray, porous granules of pure iron. But this isn't steel yet. The sponge iron gets loaded into an electric arc furnace, a massive steel vessel with graphite electrodes as thick as telephone poles. They run monstrous electrical current through these electrodes, tens of thousands of amps. Between the electrodes and the metal, an electric arc forms with temperatures reaching 6,300 degrees Fahrenheit. That's hotter than the surface of the sun. The iron melts in minutes. They add alloying elements, chromium, nickel, molybdenum, to get the exact grade of steel they need. The electricity for the furnace also comes from renewables, hydroelectric plants, and wind turbines. The molten steel glows blindingly white. They pour it into molds, let it cool. What you get are steel ingots or billets, indistinguishable in properties from conventional steel, but their carbon footprint, practically zero. The entire process uses not a single ounce of coal, not a single ounce of coke, not a cubic foot of natural gas, just iron ore, hydrogen, electricity, and water. This is fossil zero metallurgy. In August 2021, a historic event occurred. The company SSAB shipped its first batch of green steel to a customer. The buyer was Volvo. This steel was used to manufacture body parts for trucks, the first vehicles in human history made from carbon-free steel. Volvo ran tests: strength, fatigue resistance, weldability, corrosion resistance, all parameters identical to regular steel, or even better, because the process is more controlled, fewer impurities. In 2022, other companies also received batches of green steel, manufacturers of excavators, construction equipment, household appliances. Mercedes-Benz ordered a batch for use in passenger cars. SSAB announced that by 2026, it will launch the first full-scale hydrogen-based plant. Capacity, 1,300,000 tons of steel per year. By 2035, all SSAB products will be carbon-free. The company promises to cut Sweden's emissions by 7% just by switching to hydrogen. But hybrid isn't the only project out there. Right there in Sweden, they're building the H2 green steel plant, 5 million tons per year. Launch is set for 2025. In Germany, ThyssenKrupp is converting its blast furnaces to hydrogen. Austria's voestalpine fired up a pilot hydrogen plant. South Korea's POSCO is pouring billions into the technology. Even China, the world's biggest steel producer, announced it's building hydrogen plants. Governments are backing the tech with subsidies and tax breaks. The European Union rolled out a carbon tax on steel imports. More emissions, higher tariff. That makes green steel competitive. The big problem right now? The cost of green hydrogen. Hydrogen from electrolysis is still pricier than hydrogen from natural gas, but prices are dropping. Over the last 10 years, the cost of electrolysis fell by 2/3. As renewable energy capacity grows, hydrogen will get cheaper still. Another advantage of hydrogen metallurgy? It's way more compact. A traditional steel plant is an absolute monster of a complex. Coking plants, sintering factories, blast furnaces, converters, rolling mills, all of that eats up miles of land. A hydrogen facility is much tighter. An electrolyzer to produce hydrogen, a shaft furnace to reduce the ore, an electric arc furnace for melting. You can build a plant right next to your iron ore source and renewable energy, instead of hauling raw materials halfway across the globe. Swedish projects use ore from local Kiruna deposits, one of the largest in the world, and electricity from hydroelectric plants and wind farms in northern Sweden. Logistics get simpler, costs drop. Steel quality can be higher too. Direct reduction with hydrogen gives you purer iron with less sulfur, phosphorus, and other nasty impurities. That steel's better suited for high-strength applications: aviation, cars, bridges, wind turbines. Ironically, the green technology turns out to be technically superior as well. Sure, there are challenges. Hydrogen metallurgy demands massive amounts of electricity. Producing 1 ton of steel requires about 3.5 megawatt-hours of power. That's a small city's daily energy consumption. That's why projects are being built where cheap renewable energy is abundant. Scandinavia with its hydroelectric plants, Germany and Denmark with wind, Australia with sun. You also need infrastructure for storing and transporting hydrogen. It's an explosive gas. They're building special pipelines, storage tanks, safety systems. But all of this is solvable. The technology exists, the economics are starting to add up, and so is the political will. Analysts predict that by 2030, 10% of the world's steel will be produced with hydrogen. By 2050, a third or even half. That'll cut CO2 emissions by 1 billion tons annually, like removing 200 million cars from the roads. The metallurgy revolution, quiet but powerful.
And just like that, journeying from ancient blast furnaces where iron was smelted with coal 3,000 years ago, through recognizing an environmental catastrophe and searching for solutions, humanity arrived at hydrogen, the most abundant element in the universe. The very same gas that stars are made of now melts steel on Earth. Instead of black smoke from blast furnace stocks, water vapor. Instead of billions of tons of carbon dioxide, water. This is a story about how a technology that seemed unshakable was rewritten in a decade. Every time you see a new skyscraper, bridge, or car 10 years from now, know this: inside, possibly, green steel. Metal produced without harming the climate. The metal of the future, made from ore, water, wind, and sun. Black metallurgy is turning green. And this isn't just a color change, it's a paradigm shift. Humanity has proven you can build civilization without destroying the planet, even in an industry as dirty as steel. The hydrogen revolution has begun, and it will change everything.
Every second, 30 million microchips are manufactured worldwide. Smartphones, computers, cars, satellites, everything runs on one element. It's hiding in ordinary sand beneath your feet, but after an incredible transformation, it becomes the brain of digital civilization. That's silicon, the second most abundant element on Earth. Yet getting it pure is harder than extracting gold. You'll discover how sand is melted at temperatures hotter than the sun's surface, why a single gram of impurities can destroy a million chips, and how they create a material that's 99.999999999% pure. Watch till the end, because the finale reveals how a handful of sand gives birth to humanity's future. The story of silicon began in 1824 when Swedish chemist Jöns Jakob Berzelius first isolated this element from silica. He named it silicium, from the Latin silex, meaning flint. But back then, no one could have imagined that this gray steel metal would become the foundation of the 20th century's technological revolution. Pure silicon doesn't exist in nature. It's always bonded with oxygen, forming silicon dioxide, ordinary sand, quartz, rock crystal. The Earth's crust is 27% silicon. It's the second most abundant element after oxygen. Every rock, every grain of sand contains it. But turning this ubiquitous element into pure metal, that's a titanic task. The breakthrough came in the mid-20th century when scientists realized silicon could be a semiconductor. This meant it could conduct electricity better than an insulator, but worse than a metal, and that property could be controlled. That's how the idea of the transistor was born, and then the microchip. The first silicon transistor was created in 1954 at Bell Labs. From that moment on, Silicon Valley began, not just a place on the map, but an entire era. Today, global production of metallic silicon hits 9 million tons a year. China produces around 65% of all silicon, Russia about 8%, and Norway, Brazil, and the US split the rest. But this entire journey starts with one thing: sand. Not just any sand, but quartz sand, nearly pure silicon dioxide. It's mined in specialized quarries where silicon dioxide content exceeds 98%. The largest deposits of quartz sand are found in Norway, the US, Brazil, and Russia.
Massive excavators scoop up white sand that looks like sugar and load it into dump trucks. This sand heads to a metallurgical plant where modern-day alchemy begins. Inside a giant industrial hangar sits a furnace that looks like a spaceship, an electric arc furnace. It stands 33 feet tall, 20 feet across. Inside, 3 massive graphite electrodes, each as thick as a telephone pole. When tens of thousands of amps surge through them, an electric arc forms between the electrodes, a miniature lightning bolt that hits temperatures of 3,600 degrees Fahrenheit. That's hotter than volcanic lava, hotter than the surface of some stars. Into the furnace goes quartz sand mixed with carbon, wood chips, coal, or petroleum coke. Carbothermic reduction begins, a chemical reaction where carbon rips oxygen away from silicon dioxide. The formula is simple, but the process? Pure hell. Silicon dioxide plus carbon at 4,000 degrees Fahrenheit turns into liquid silicon and carbon monoxide. The furnace roars like a jet engine. Inside, a fiery inferno rages. Molten silicon's heavier than slag, so it sinks to the furnace floor, forming a silvery lake of liquid metal. Every few hours, workers in fireproof suits open the tap hole, an opening at the bottom of the furnace, and molten silicon pours out in a blinding river of fire into special ladles. The stream's temperature? 2,700 degrees. The air around it shimmers with heat. Silicon gets poured into cast iron molds, where it slowly cools, turning into gray metallic ingots. This isn't pure silicon yet. This is metallurgical-grade silicon, about 98% pure. It contains impurities: iron, aluminum, calcium. For metallurgy or silicone production, that's good enough.
But for electronics, absolutely not. Microchips need silicon that's 99.999999999% pure. That means for every billion silicon atoms, there can be no more than 1 impurity atom. Reaching that level of purity is a task that borders on magic. Metallurgical-grade silicon heads to a chemical plant where the purification process begins. The silicon is crushed into powder and mixed with hydrogen chloride at temperatures of 600 degrees Fahrenheit. This creates trichlorosilane, a volatile, toxic liquid that boils at 90 degrees. It's an intermediate compound, but it's critically important. Trichlorosilane passes through a series of distillation columns, giant towers as tall as a 10-story building. The liquid boils, evaporates, condenses, boils again, and with each cycle, impurities get left behind.
After 100 cycles, you get trichlorosilane that's 99.9% pure. Now you need to turn it back into pure silicon. That's where the Siemens process comes in, one of the most beautiful and complex in metallurgy. Inside a sealed reactor, they install thin silicon seed rods. Purified trichlorosilane is fed in along with hydrogen and heated to 2,000 degrees Fahrenheit. At that temperature, the trichlorosilane breaks down and pure silicon deposits onto the seeds, building them up layer by layer, atom by atom. The process runs for several days. In that time, those thin rods grow into thick cylinders up to 8 inches in diameter and weighing up to 660 pounds. They look like giant gray icicles. This is polycrystalline silicon, the purest material humans have ever made. Purity reaches 11 nines, 99.999999999%. A single kilogram of this silicon costs anywhere from $20 to $50, tens of times expensive than metallurgical grade. The polycrystalline silicon gets chopped into chunks and shipped off to single crystal manufacturing plants. Here's where an even more remarkable process begins: growing a crystal. Yeah, growing it, like a plant. Chunks of polysilicon get loaded into a quartz crucible and melted at 2,592 degrees Fahrenheit, silicon's melting point. What you get is a mirror-smooth lake of molten metal. Then they slowly lower a seed crystal into the melt, a perfectly oriented piece of single crystal silicon. And they start slowly rotating it while simultaneously pulling it upward at a rate of a few millimeters per hour. The molten silicon crystallizes onto the seed, atoms locking into a perfect crystal lattice, copying the seed's structure. The process is like pulling a giant sugar thread from syrup, except instead of syrup, it's molten metal at nearly 3,000 degrees Fahrenheit. After several days, a cylindrical single crystal grows from the melt, an ingot up to 6.5 feet long and about a foot across. It weighs up to 660 pounds. This is one continuous crystal where all trillions upon trillions of atoms are arranged in perfect order. This cylinder is called a boule or ingot. It's gray, smooth, with a metallic sheen. One of these ingots costs tens of thousands of dollars. The boules are sent for cutting. They're clamped into special machines and sliced by diamond saws into thin discs, wafers. Each wafer is about 700 micrometers thick, less than a millimeter. Cutting moves at a few centimeters per hour because the slightest vibration will shatter the fragile crystal. A single boule yields several thousand wafers. Each wafer gets ground and polished to a mirror finish. The surface must be absolutely flat, deviation no more than 1 nanometer across an area of 12 inches. That's like leveling a football field to within the thickness of a human hair. These finished silicon wafers are the foundation of all microelectronics. Photolithography imprints circuits onto them, billions of transistors just a few nanometers in size. A single 12-inch wafer can hold up to 1,000 processors or tens of thousands of memory chips. After etching, doping, and depositing metal contacts, the wafer gets diced into individual chips. Each chip is a complete microprocessor, ready to become the brain of a smartphone, computer, or car. The entire journey from sand to processor takes several months and passes through dozens of factories across different continents. This entire incredible journey, from a handful of sand in a quarry to a microscopic chip in your phone, shows how far humanity has come in understanding matter. Silicon gave us computers, the internet, artificial intelligence, spacecraft. Every day, 7 billion people hold devices in their hands that work because of this element. The global silicon wafer market exceeds $15 billion a year, and the microchip market, over $500 billion. All of it built on that same gray metal that was once ordinary sand. Silicon became the foundation of the digital era. Without it, there'd be no computers, no smartphones, no internet. We live in a silicon civilization without even thinking about it. And every time you touch your phone's screen, remember, beneath the glass, billions of transistors are working, made from that very same sand you walk on every day.
Every hour across the globe, dozens of nuclear reactions, but only a handful know that at the heart of every atomic bomb lies a material capable of destroying a city in seconds. This isn't just a weapon, it's a miniature star, crafted by human hands. You'll discover how ordinary uranium births an explosion with the force of 1,000 suns, why sand in New Mexico turned to glass, and what happened to an island that no longer exists. And most importantly, what secret hides inside a nuclear warhead? Watch until the end, because the finale will change how you see the modern world. Back in the day, when the world was just learning to hear the voice of the atom, a few curious minds peered inside the invisible. into the heart of matter. Those were the years when science was feeling its way forward, but with great determination. German chemist Otto Hahn, along with Fritz Strassmann, like alchemists of a new world, discovered that uranium could split. It was as if ice cracked on a river, behind which a giant lay sleeping. While Europe prepared for war, a group of people secretly gathered across the ocean, later to be called the Masters of Atomic Fire. In the New Mexico desert, the Manhattan Project began. Ordinary physicists, Oppenheimer, Fermi, Teller, became the creators of the greatest force humanity had ever seen. In the summer of 1945, beneath the clouds of dawn, the first nuclear bomb exploded. Sand turned to glass, sky to fire. And in the absolute silence, one scientist whispered, "Now I am become death, the destroyer of worlds."
But the story didn't end there. Days later, Hiroshima and Nagasaki became pages of grief. And just when the world thought it had seen everything, the USSR answered. Under Igor Kurchatov's leadership in 1949, the first Soviet atomic bomb detonated. A decade later, the Tsar Bomba. Its power could level a city the size of Paris. History's irony. Nuclear weapons became not a sword, but a shield. Their existence forced enemies to talk. Ideas of security, control, diplomacy became more important than warfare. For the first time, humanity faced massive questions. Can we negotiate so everyone survives? That's how deterrence doctrine was born. Don't attack, because you know attacking means catastrophe. And while this balance is far from perfect, it's delivered decades without global war between superpowers. An entire era. Cold, anxious, but without mass battlefronts. Nuclear research sparked whole new industries: nuclear power, reactors on submarines, medical diagnostics. Even space projects got a boost from understanding the atom. To create the most terrifying thing, we learned to grasp the most complex. Yes, nuclear weapons are dangerous, but they're also a mirror of human wisdom. We built something incredibly powerful and chose not to use it on a massive scale. This is a story about power we decided to restrain, about science that taught us not to dominate, but to coexist. Deep in laboratories, where lamplight dimly illuminates blueprints, the path to building a nuclear bomb begins. This isn't just assembling metal, it's modern-day alchemy, where every gram of material holds the power of 1,000 suns. It all starts with uranium or plutonium, isotopes capable of sustaining a chain reaction. But natural uranium is mostly uranium-238, which won't work, so they enrich it, separating out the 235 isotope using centrifuges, where gaseous uranium spins at insane speeds. Plutonium is artificial. It's produced in nuclear reactors, where uranium absorbs neutrons and transforms into plutonium, the stuff you need for a nuclear bomb. The appearance of a nuclear bomb often resembles a classic aircraft bomb, a streamlined metal casing engineered for stable descent from high altitude. In a massive hangar where the walls ring with the echo of metal, the air smells of hot steel and oil. Here begins the birth of the shell that must contain the heart of an atomic explosion. From the glowing throat of an industrial furnace flows a stream of metal, special steel, reinforced with nickel, chromium, and manganese. Its temperature exceeds 1,000 degrees. Summer sunlight looks pale compared to this fire.
Masters in protective suits with transparent face shields watch the forming process. Steel sheets bend into streamlined shapes under presses exerting hundreds of tons of force. Before their eyes, an elongated body takes shape, resembling a water droplet frozen under the pressure of the heavens. Next, mechanical arms mill the internal partitions, cut openings for tail stabilizers and locking mechanisms. Every fraction of an inch, the result of meticulous calculation, because balance during descent depends on it. After this, the casing undergoes a strengthening ritual, immersion in an anti-corrosion bath, treatment with polymer coating, application of matte paint. The color? Dark green, like a military shadow in the twilight of pine trees. And finally, testing. They drop it from height, strike it with hammers, spin it in a wind tunnel. Only after passing all trials is the casing ready to receive its lethal payload.
A quiet lab, half light, a faint smell of ozone, something heavy hangs in the air. In front of you lies an open nuclear bomb, its metal casing removed, its insides, like an organism, laid bare. There's nothing extra here, no shine, no decoration, just function, just explosion. At the center, a smooth, perfect sphere. It looks like a dull meteorite. This is the nuclear core. Plutonium-239, cold and deadly, or uranium-235, heavy as a planet in your palm. Its shape, mathematical perfection, polished down to microns. Around this sphere, an entire symphony of pressure. Composite explosives, layer upon layer, like a flower turned inside out. Their job isn't simply to detonate, but to force the explosion inward. Like hands clenching to the limit, these explosive lenses must create implosion, uniform, merciless compression that drives the material supercritical.
If even 1 second lags, the whole contraption becomes a heap of meaningless metal. And at the very heart of this implosion orchestra, the initiator, a tiny device waiting for its moment to release the first neutrons. Polonium and beryllium interact, creating a minuscule storm capable of triggering the irreversible. That's where the chain reaction begins, a match to an atomic forest. Then, the tamper layer. Heavy as a shadow, it wraps the bomb's core not for protection, but for containment. Uranium-238 or tungsten, not active, but absolutely critical. Their job? Delay the neutrons, force them back like an echo in a cave. Everything depends on this. The duration of the blast, its power, its climax. In the tail section, the brain. Automation, electronics, wires and sensors. Barometers waiting for altitude, radars tracking the ground, batteries sleeping, ready to wake. This is where it's all decided, when everything happens, above the city, in the air, after the drop. Without this nervous system, the blast would be an accident. But here, it's a calculation. If you look at the entire structure in cross-section, it resembles the layers of a planet, like chapters in an encyclopedia of force. The outer shell, smooth and cold. The explosive layer, mathematically arranged. The tamper, an invisible guardian. The core, like a seed of what's to come. And at the very center, a spark, sleeping until awakened. Over 62 years, the world witnessed 2,065 nuclear explosions. 5,224, that's not the number of nuclear explosions, but an approximate estimate of the entire U.S. arsenal, including active, reserve, and decommissioned warheads. Now, the number of nuclear tests that the United States conducted from 1945 to 1992 totals 1,154 detonations.
Each one is a separate page in the history of power, fear, and science. The first blast, Trinity, July 16, 1945, in the New Mexico desert. It was the beginning of an era when atomic energy became a weapon. Then came Hiroshima and Nagasaki, the only instances of nuclear weapons used in combat. In the decades that followed, the U.S. tested bombs at Enuatak and Bikini atolls, in Nevada, underground, in the atmosphere, over water. The blasts had different purposes:
testing new designs, demonstrating power, studying effects on equipment and living organisms. Yield varied, from a few kilotons to 15 megatons, like in the Castle Bravo test of 1954. In 1952, the US conducted its first thermonuclear test, Ivy Mike. This wasn't just a bomb anymore, but a miniature star created by humans. The explosion wiped out an entire island. In the 1960s, testing became routine. The US tested warheads for missiles, aerial bombs, even neutron charges that had minimal blast waves but maximum radiation. The last official detonation happened on September 23, 1992, after which the US declared a moratorium, but the arsenal remained. It gets modernized, adapted, stored. Some warheads are on submarines, some on strategic bombers, some in NATO storage facilities. These explosions aren't just technical events. This is a story about how humanity learned to control the energy of stars and put it in the service of fear. But it's also a reminder that the power capable of destroying civilization sits under the control of those who understand the price of using it. And as long as this balance holds, the world continues to exist on the edge of the abyss, but doesn't fall in.
Every year, the world produces over 100 million cubic meters of MDF boards. Picture this. If you laid them out as a road 30 feet wide, you could wrap it around the entire planet at the equator, and that's every single year. But few people know that these perfectly smooth panels aren't born from wood, but from trash, sawdust, scraps, and old newspapers. How does ordinary dust transform into a material that revolutionized the furniture industry? And what secret lies in a process where steam, resin, and hundreds of tons of pressure turn chaos into perfection? Stick around till the end. You'll see what's hidden behind every gleaming piece of furniture in your home. The base for MDF isn't solid logs, but what used to be considered trash: sawdust, wood chips, scraps, and even old waste paper. It's a triumph of resource efficiency. These mountains of wood waste arrive at the factory and first get thoroughly cleaned. Powerful magnets pull out any metal contaminants, nails, staples, while screening systems remove sand and stones that could damage expensive equipment. After that, the raw material goes into a huge vat where it's washed and steamed with hot steam. This isn't about cleanliness. The steam is there to soften lignin, nature's glue that holds wood fibers together. Now begins the most critical stage, the one that sets MDF apart from its rougher cousin, Particleboard. The prepped softened chips get fed into a machine called a defibrator or refiner. Picture two giant metal discs, like millstones, spinning toward each other at incredible speed. Their surfaces are covered with an intricate pattern of sharp ridges and grooves. The wood pulp gets caught between these discs, and they literally comb it apart into its tiniest components, tearing it into individual wood fibers. This isn't chips anymore. It's something like fluffy, damp cotton or wood flour. We've just deconstructed wood down to its basic building blocks. Next, this fibrous mass needs to be dried, but it has to happen fast, before the fibers start clumping together, so they get blown into a long, hot drying tube. A stream of hot air catches the fibers, and as they fly through this tube, all excess moisture evaporates out of them. And right here, while the fibers are still hot and swirling in this vortex, the next critical stage happens: resin application. A fine mist of binding agent gets sprayed into the airstream through special nozzles. This is urea formaldehyde resin, our glue. This mist coats every tiny fiber, covering it with a thin, sticky film. It's an incredibly efficient method, guaranteeing perfectly even glue distribution. Interesting fact, Urea formaldehyde resin was first synthesized in the 1920s, but it only started being used on a massive scale in wood panel production after World War II. Now this resin-saturated, dry, and fluffy light mass is ready to become a board. It goes into the forming machine. The stream of fibers settles onto a wide moving conveyor belt, forming a thick, loose, and perfectly even mat. Special rollers compress it slightly, and giant knives cut it into pieces of the required length. It already looks like the future board, but for now, it's just a thick, soft mattress of wood fluff. And then comes the climax, hot pressing. This loose mat rolls into a giant press. It might be either a multi-story press that simultaneously compresses an entire stock of boards, or a continuous press that looks like giant caterpillar tracks. And here, two powerful forces act on our mat at once. First, colossal pressure. The press plates squeeze our loose mattress with a force of hundreds of tons, reducing its thickness several times over and forcing out all the air. The wood fibers squeeze together tightly, creating an incredibly dense structure. Second, high temperature, 400 degrees Fahrenheit. This heat does two things. It activates the resin, causing it to polymerize and bond the fibers into a single monolith, and simultaneously evaporates any remaining moisture, which escapes from the board as hissing steam. After just a few minutes in this steel embrace, the loose mat transforms into a solid, dense, perfectly flat, and still very hot MDF board. Pressure in modern presses can reach 700 pounds per square inch. Imagine an adult cow standing on an area the size of a postage stamp. After pressing, the hot boards can't just be stacked. They need to cool down to relieve internal stresses. They're placed in a special fan cooler that looks like a giant card catalog, where they slowly cool down, fanned by air. Once the sheets have cooled, it's time to give them that finished look. First, they're stacked in tall piles and left to rest for a few days. This stabilizes their internal structure. Then each sheet runs through a sanding machine. Picture a giant belt sander with multiple heads. Wide abrasive belts strip away a thin surface layer from both sides, bringing the sheet to a perfectly precise thickness, say 16 or 18 millimeters, and creating that famous paper-smooth surface. And the final touch? Cutting. Massive saws slice the large production sheets into standard commercial formats. After that, every batch goes through strict quality control. Density, strength, thickness, and surface quality all get checked. Modern MDF panels have a density of 37 to 50 pounds per cubic foot. That's 1.5 times denser than natural pine. The finished, perfectly smooth panels get labeled, packed up, and shipped off to furniture factories, where they'll become the foundation for elegant and stylish pieces in our homes, silently demonstrating what a noble journey ordinary wood dust can take. The global MDF market? It's a giant machine churning out more than $25 billion a year. And this machine isn't planning to stop. Forecasts say it'll grow 6% annually. That means demand for this smooth material is absolutely insane. So, who's the head chef in this kitchen? The undisputed king, China. They produce over 50% of all the MDF in the world. Chinese factories run around the clock, churning out millions of cubic meters of boards for domestic use and export. But Europe's no slouch either, with powerhouses like Germany, Poland, and Turkey cranking out millions of cubic meters of high-quality board. German manufacturers are especially famous for innovative technology and strict environmental controls. Now let's talk volume. Every year, the world produces about 100 million cubic meters of MDF. That number is so massive, it's impossible to picture. Let's try anyway. Imagine a road. If you took all that MDF and laid it out as a road 30 feet wide and 10 inches thick, you could wrap a belt around the entire planet at the equator. Generously, an endless stream of material transformed into furniture, doors, and panels for our homes. What's fascinating is that MDF has unique properties you won't find in natural wood. No knots, no cracks, no voids. You can mill it, creating complex decorative elements that would be impossible or way too expensive with solid wood. That's exactly why MDF became the #1 material for kitchen cabinet doors, raised panel doors, and decorative trim. Plus, MDF holds fasteners incredibly well. Screws grip far more securely than in standard particle board. And that smooth surface? Perfect for paint. It goes on evenly, no fuzz, no grain, creating a finish that looks like plastic or even glass.
Environmentalists often criticize MDF for using formaldehyde resins, but modern technology allows manufacturers to produce E0 and E-half grade boards, where formaldehyde emissions are lower than in natural wood. And so having journeyed from a pile of sawdust and scraps through a steam bath, defibrator, pressing under hundreds of tons of pressure, and final sanding, this amazing material emerges. Dense, strong, perfectly smooth, and ready to become part of our homes. From humble kitchen cabinets to luxurious carved facades, from simple interior doors to intricate decorative panels, MDF works everywhere, the silent hero of modern interiors. It doesn't demand admiration, doesn't seek glory, but it's what makes our homes cozy and beautiful. And now you know its story, from trash to treasure, from wood dust to a masterpiece of engineering.